Welcome everybody to the INQA seminar for 28th of January 2025. It gives me great pleasure to introduce today's speaker, who is Sebastian Nagies. Sebastian's a PhD student at the University of Trento in northern Italy, and Sebastian will talk to us about boosting quantum annealing performance through direct polynomial unconstrained binary optimization. Over to you, Sebastian.
Yeah, thank you very much, and thank you for the invitation to speak here. And I'm talking about this work which we put on the archive last month, and it came from a collaboration of our university and our group and Electron, which is a German startup building a trapped ion quantum computer. And the people I'm working with I'm a PhD student in the group of Philipp Hauke. And the main part of the work was done together with Kevin Geyer, who was a postdoc in our group, but is now in Abu Dhabi. And from the Electron team, we had 3 people that contributed to the work with Javid, Akram, Dimitrios Bantanos, and Michael Johanning. Okay, and I'm going to start with some basics, but I guess here for this audience, most people are familiar with quantum annealing. But the basic premise that we have is that we want to solve some problem which we want to encode in the ground state of a cost Hamiltonian. And we reach this ground state in the cost Hamiltonian by starting in the simple ground state of a driving Hamiltonian, and then tuning the parameters, the coefficients of the driver and cost Hamiltonian slowly, so that at the end, if we tune them slowly enough, we end up in the ground state of the cost Hamiltonian, which encodes the solution to our problem. And how slowly do we have to tune the parameters, which is roughly given by this adiabatic condition, which basically tells you that delta E, which is the minimal energy gap encountered during the annealing protocol, is small, then the time that I have to run my annealing protocol has to be large. And also here, this matrix element is usually this is scales only polynomially, so usually the adiabatic runtime is only determined by the energy gap of the problem. And for this energy gap, we say that the problem is hard to solve if the gap closes exponentially, which corresponds to a first order phase transition, or it is an easy problem to solve if we only have a polynomial gap closing. Okay, what are the kind of problems that we solve with quantum annealing? Typically, we consider so-called quadratic unconstrained binary optimization problems, which here in classical variables corresponds to a cost function f, which is given at most with quadratic interactions of classical binary variables, which can be 0 or 1. And this classic cost function can be easily translated to a quantum Hamiltonian by introducing spins for each classical variable, and so translating this cost function into a Hamiltonian with 2-body interactions and local fields, where the ground state of this Hamiltonian then encodes the solution to our classical optimization problem. And finding this ground state is generally hard because it's kind of an easy spin-glass system with a very rough energy landscape with many local minima. And the finding the global optimum is a hard problem generally. So what we wanted to do in this work, compare not just quadratic cost functions here at the top given QUBO, but also higher order cost functions, QUBO, which stands for polynomial unconstrained binary optimization. And specifically, we consider, or what I will talk about now is only third order QUBOs. So at most, we have 3-body interactions of the classical variables next to 2-body and local fields. So the cost Hamiltonian of such a QUBO would look like this here in the bottom, with 3-body interaction, quantum spins, 2-body interactions, and local fields. And we want to, the goal of this work was to compare the performance if we have one single problem instance and encode it either into a QUBO form, which is the usual way, or into a PUBO form, the equivalent problem, and compare their annealing runtimes or the performance that we can expect. Okay, then the question is, if we compare these PUBO and QUBO problem instances, how do we measure, or what is the quantity that says us how much faster the QUBO formulation or the PUBO formulation is versus the other? So if we start here at the top from the adiabatic condition, write it in a bit more simplified form, where we just have here the minimal energy gap between the ground state and first excited state, and V is the matrix element here, which usually only scales polynomially. So, and then if we have a hard problem where this energy gap closes exponentially in system size n, then the annealing time, or T sweep, is dominated by this gap closing of the energy gap. So for these hard problems, we can then formulate the ratio of the adiabaticity time or sweep times of the QUBO versus the PUBO formulation like this, with this ratio, where we have the exponential scaling, where we compare the exponential gap closing alpha Q versus the exponential gap closing of the PUBO problem, alpha P. And then here we have, in front of this exponential scaling, we have some constants, where we have the energy scale of the three-body detections, the typical energy scale, versus the energy scale of the two-body detections. In practice, usually the three-body detections are much weaker. And then we have also here some, here in the bottom right defined, some dimensionless energies in units of the J2 of the three-body or two-body interaction respectively. Okay, so this is what we mainly use to discuss the speed of the PUBO formulation versus the QUBO formulation. Okay, so the problem that we actually mostly considered in this work is the standard three-set problem, which has multiple reasons. We also, in our paper, gave some examples of other problems which can be easily formulated as a PUBO, but the three-set problem has the simplest possible form and has only three-body actions at most. Okay, so what is the three-set problem? We are given n classical Boolean variables, x1 to xn, and we have given a number of m logical clauses, c1 to cn. And each clause has, for three-set, a distinct form, where we have each clause contains three classical variables, which are connected by disjunction or logical OR operations. And these are negations of classical variables. So in order for this example clause to be true, we have to have either x1 is true, or not x2 is true, or not x3 is true. And this has to be then for three-set fulfilled for all n clauses simultaneously. So three-set asks this Boolean formula is satisfiable with some assignment of classical variables. And this was one of the first problems proven to be NP complete. And if we look at like a very simple version here with just 4 different classical variables and two clauses, then we can, here on the right, have a truth table where we can put in different true or false or 0 or 1 values for the classical variables and see if our whole Boolean formula evaluates to true or false. And in the simple example, we see that there are many, many different possibilities to assign truth values and get a true outcome. But what we are mostly interested is in the hardest instances, the hardest instance of three-set, which are expected to have this exponential gap closing. And in the literature, it is known that there's a kind of phase transition, where if we vary the ratio of the number of logical clauses to the number of variables, then we have some point where left to that point, the instances are almost certainly satisfiable, while to the right, they are almost certainly unsatisfiable. And so if we look at instances around this phase transition point, there we have a good probability to find very hard to solve instances, which usually means that the instance has one unique solution. Okay, so how can we encode three-set into a PUBO or a QUBO? So we look here at this simple example again at the top, and the most straightforward way to encode it into a class or a quantum cost function is actually as a PUBO of third order. So we can translate each clause. Here, for example, the first clause can be translated into this term of the classical cost function. And the second clause can be translated into this term of the classical cost function. And we can do that for every clause that we have in the problem. And these terms in the cost function give us an energy penalty if the corresponding clause is not fulfilled and otherwise evaluate to 0. And then we can again introduce for the classical variables quantum spins and translate it to a Hamiltonian which contains 3-body interactions and 2-body interactions. This costs us for n classical spins. This costs us n qubits. So, okay, and how would we encode it into a corresponding QUBO, which we could, for example, then feed to the D-Wave machine or whatever. There are many different ways known to translate this into QUBO. There's, for example, a well-known map to a graph coloring problem, which would use the number of 12 n spins. If we have n classical variables, it would use 12 n qubits. But the most efficient or straightforward mapping of the 3-set into a QUBO would be to start with the PUBO formulation and then reduce all 3-body interactions to 2-body interactions. And we can do that by introducing additional ancillary variables or slack variables. And in this way, for hard instances, you would expect to need around a number of 4n qubits. So we have, even without considering any speed ups in terms of adiabaticity time, we have a spatial or a resource savings when formulating a problem as a QUBO. And this also holds for many other problems which can be formulated as a QUBO. For example, the traveling salesman problem with time windows or a hypergraph quelling problem are also equally conveniently formulated as QUBO, saving qubits. But here we concentrate on this 3-set problem. So, okay, how exactly do we introduce these slack variables in formula as a QUBO? This can be done like so. We have our Hamiltonian with 3-body interactions, and then for each 3-body interaction term, we encounter the Hamiltonian. For example, here, x1, x2, x3. We introduce one ancillary variable. In this example, we introduce a 4th ancillary variable, x4, which should be equal to the product x2, x3. So we can then rewrite our 3-body interaction in this 2-body interaction. But to enforce this inequality that x4 is always equal to x2 times x3, we need to add to the Hamiltonian additional penalty terms, which are given here in the bottom. And these penalty terms, or this penalty term evaluates to 0 only if x4 equals x2 times x3 is given. Otherwise, there's a positive energy penalty. And introducing these additional slack variables is itself an NP-hard problem. But for the small system sizes that we considered here, we basically brute force the optimal solution to find the best mapping to a QUBO. So, okay, now we have our preset and we can write as a QUBO and as a QUBO and compare the two formulations. Okay, to generate the 3-set problems, the hard 3-set problems that we want to discuss, we took from the literature two different solvers, 2 different generators to generate classical instances. One on the left is the tough set generator, which basically means that you just completely randomly generate an instance around this phase transition point where you expect hard instances. So you just, for a given number n of classical variables, you generate a number approximately 4 times n of logical clauses randomly. And then after that, you check classically if this instance has a unique solution. And if yes, you post-select for it, so you get hard instances with unique solutions. The other generator doesn't need post-selection, but constructs explicitly instances with unique solutions. But the difference to the left generator is just that we need fewer logical clauses to construct these instances. So while the left one needs 4 n logical clauses, the right one needs only n plus 6 logical clauses. So it scales approximately linearly with the system size. Okay, and then one important thing that we have to keep in mind, if we look at an annealing schedule here at the top, with the left term is the driving Hamiltonian with the usual choice of sigma x, and the right one is the cost Hamiltonian encoding our solution. And we have a scaling of the cost Hamiltonian is in units of J, and the driving Hamiltonian is in units of Hx. So then we usually set for our numerics Hx equals to J. I will later also discuss this in a bit more detail. But for this J, we have to differentiate between the PUBO and the QUBO formulation. So this is the energy scale of the system, which usually is different for PUBO and QUBO formulation, because for three-body actions, the three-body actions are usually much weaker than two-body actions, and so they set the relevant energy scale of the whole system. And if you have a QUBO, you only need to consider the two-body actions, and then the two-body actions set the relevant energy scale. Okay, so here we look at some example annealings or energy spectra during an annealing protocol for the different generators. For example, here at the top left, we have for the Tafsir generator, the PUBO formulation. And then we have during the annealing protocol, starting on the left with the driving Hamiltonian, ending with the cost Hamiltonian. And we look at the ground and first excited state and see where the minimal energy gap occurs. And then on the bottom, we have the equivalent QUBO formulation obtained via introduction of these ancillary variables, like I discussed before. And here the same thing for these unique PT1 instances, PUBO and QUBO formulation. And then on the right, just for completeness, I also show one instance how it looks like if we would have a problem with a trivial solution where we don't have any gap closing. But as we will see for these left two cases, for these two generators, we actually observe this exponential gap closing of the minimum energy gap. Okay, before I go to show you the scaling results, I want to briefly discuss this choice that we used for numerics, like Hx equals to J. And then there's also another choice that we have to make, namely how large do these penalty terms, which we have to introduce in the QUBO formulation, how large do we have to scale them for optimal annealing performance? Because if we compare the PUBO and QUBO formulations, we want to have the most fair comparison possible. So choose these parameters in a way that mostly favors the QUBO formulation the most. So for the first case, so for Hx, we have done some numerics. So if we see this energy scale Hx over J, which we vary. And then we look in the red curve on the minimal energy gap of the system, which increases monotonously with the energy scale Hx. So one would think that you could increase annealing performance as much as you wish by just tuning up Hx. But if you actually look at the adaptivity time of the protocol, then we have a clear minimum, which is around Hx equals J. So this choice is reasonable, which we made. Then for the second problem, if we do go from the PUBO formulation to the QUBO formulation and introducing these ancillary variables, we have the following problem. We have this cost Hamiltonian, which now contains the problem Hamiltonian plus these constraints that we introduced. These are scaled by some lambda, and this lambda has to be chosen large enough so that it's never worth it to violate the constraints, basically. But at the same time, tuning this lambda or varying it changes the minimal energy gap on the protocol, and so also the annealing performance. So, and if you here at the top right, look at this plot, vary this lambda, and look at the minimal energy gap during the problem, then we see that we have a clear maximum where we have the best performance or maximum energy gap. And the black line denotes the point where our lambda is too small, and at this point, the ground state of the cost Hamiltonian is no longer a valid solution of our problem. So lambda has to be chosen larger than this. And then the dashed line denotes the choice of lambda that we made for numerics. So this is not quite at the optimum, but not far from it. But we see also this optimum varies a bit from instance to instance. And so for some instances, it is a bit shifted to the right. So this is actually a conservative choice, which made a lot of sense for our numerics. And okay, to understand the behavior of this curve, we can look at the energy spectrum during by varying this energy factor lambda. So here we see the first 30 eigenvalues of h cost plotted, and then color-coded are in green eigenstates which fulfill all constraints, so would be valid solution, and red are eigenstates which violate at least one constraint. So we see for very large energy factor lambda, the ground state and first excited state are both fulfilling all constraints. This means that they don't get any energy cost from this h constraints. And so basically by tuning lambda up further and further, you don't get any advantage. But if you tune lambda lower, at some point, the first excited state is no longer a state which fulfills the constraints, and the energy gap goes down. But this would still be no problem as long as the ground state is a state fulfilling the constraints. But at some point here, the black dashed line corresponding also to the same black line above is the point where the first energy violating state crosses the ground state which encodes the actual solution. And at that point, your problem would no longer be valid. Okay, but for our choice, we have this safe choice of lambda. So for us, always the ground state that we find is a valid ground state. Okay, now to the actual scaling results. If we look here at the top plot, we have plotted over the system size, the number of classical variables in the three-set problems. And on the y-axis, we have the mean minimum energy gap of 200 randomly generated three-set samples or three-set instances. And with a log plot, so we have a clear exponential scaling with the system size. And we see here blue curve is the PUBO formulation, and an orange curve is the equivalent QUBO formulation. And okay, what we see for this top one with the unique PT1, which are these benchmark generators generating specifically constructed instances with a unique solution. But for this, we basically see the same exponential gap closing, but with a constant offset. But for the tough set instances, the situation looks very different. So here we have a clear slower exponential gap closing for the PUBO formulation than for the QUBO formulation. So the energy units on the y-axis are again given in terms of the relevant energy scales, which is for the PUBO formulation, this J3, or the three-body interaction strength in the system. And for the QUBO formulation, this J2, which is the two-body interaction strength. And okay, if we look at the actual fit data for these exponential gap closings, we see for the PUBO formulation, alpha is the coefficient of the exponential gap closing. We see that for unique PT1, they are very similar. Within the arrows, they could be the same. But for...
Sorry, you froze there. We lost you for maybe around 30 seconds.
Ah, okay.
Maybe
do you hear me now?
Yeah, I can hear you okay now.
Ah, okay.
Let me explain this again. Sorry about that.
Okay. Okay, I was just saying that okay, the energy scales on the y-axis are given in terms of the three-body interaction strength for PUBO or the two-body interaction strength for QUBO, respectively. And if we now look at the fit data, we also see clearly that for the unique PT1 generator, we have approximately the same gap closing for this alpha coefficient. Within the error bars, they could be the same, or there could be a very small difference. But for the tough set generator, there's a very clear, distinct difference in the gap closing. So the gap closes much slower for the PUBO formulation than for the QUBO formulation. And okay, we can then calculate how much faster is the PUBO version than the QUBO version, where we have this formula, which I introduced at the beginning. And now we just have to plug in our numerical fit data for the epsilons and the alphas. For the VQ and VP, which are the matrix elements of the adiabatic theorem, they can be computed numerically. They are around 0.5 to 1, depending on the instance, and they scale at most polynomially. And then the J3 versus J2. So this is a relevant point. How large is the three-body interaction compared to the two-body interaction? And okay, if you look at some systems, the three-body interactions are generally very weak. For example, in this other work, we looked at a trapped ion computer and calculated how perturbatively, how strong three-body interactions are that occur in the system, and they're usually negligible. But I mean, there are some very specific and proposals and specific circumstances where you can tune three-body interactions also to the same strength or comparable strength to two-body interactions. But for this comparison, we looked at a more straightforward way, where we just considered a quantum gate circuit, where we want to implement three interactions of the form here, S1, S2, S3, three-body interaction term, and we can always implement this three-body interaction term with a circuit in A, composed of 4 C0 gates plus a rotation around Z. And then we can further, if we want, decompose the C0 gates into RZZ rotations plus single qubit gate, which for some hardware it's more or is the native gate set for some trapped ion qubit hardware. But basically, the main point is for three-body interactions, we need 4 two-body interaction gates. So if we assume that single body rotations are negligible in duration, then we can assume that in this case, the ratio of J3 to J2 is approximately 1/4. And this is the value that we used for the calculations now. And okay, if we now plug this in the speedup, we see for the unique PT1 instances, we see this constant speedup factor of 6 or so if VQ over VP is around 0.5. With a very small exponential speedup or none within the error bar, it could also be 0. But at least we have a factor of 6 in the speedup. But if we look at the tufted instances, which again, to remind you, are basically just randomly generated instances around the phase transition point where we expect hard instances, then we can see a clear exponential time advantage for the PUBO formulation. And so if we look at this, for example, for n classical variables, the PUBO formulation would already be 2 orders of magnitude faster than the QUBO formulation. And then this increases by another order of magnitude for each additional 5 variables in the classical problem. So this would be, for these kinds of problems, a clear advantage. And at last, a quick aside, also interesting is to note the comparison of this scaling with state-of-the-art classical set solvers. And it is generally known that for unique 3-set can always be solved in around 1.3 to the n time. But if we look at the adiabaticity time that we observed for PUBO for these tough set instances, we actually find an adiabaticity time which scales better with 1.19 to the n. But okay, I mean, this looks promising, but it has to be taken with a very large grain of salt, because one, this adiabaticity time, which comes from the adiabatic condition, is a very, very rough estimate of the actual annealing time that we require. So there are other better bounds on this time. And second, this classical value of 1.3 to the n is valid for every possible instance. And this adiabaticity time we only saw for the specific case of these tough set instances, and not, for example, if you look at the unique PT1 instances, there we get an adiabaticity time which scales around 2 to the n, so basically like comparable to classical brute force solving. But it's still an interesting result that we also plan to look further into. Okay, and then to summarize, we saw that the PUBO formulation for some specific classes of 3-set problems can be solved exponentially faster with quantum annealing than the equivalent QUBO formulation, which you usually consider when you submit your problem to D-Wave or another hardware. And also, when you directly compare the PUBO for performance with classical solvers, it seems promising, or it seems at least interesting that the adiabaticity time scales this favorably. And here, the top right is the paper, which where a bit more details are also included if you're interested. And what we're currently working on is implementing quantum annealing protocols on the actual electron trapped ion quantum computer hardware. And there we consider how error sources and problems that one encounters on actual hardware affect the quantum annealing protocol, or what we can do to circumvent it. Thanks for your attention.
Great, thank you very much, Sebastian. A lot of interesting things there to think about. And I guess if we have some questions, please do unmute yourself or raise your hand or just speak up. So maybe I'll start with a question. So in general, well, your problem is k-sat, let's call it that. K equals 2, no, sorry, k equals 3. And the third order PUBO worked pretty well when k equals 3.
Yes, yes.
I assume that if I go to k equals 4, that the fourth order PUBO.
Yes. I mean, okay, to study it, the problem is, okay, if you go to fourth order, then you need Hamiltonian with fourth order interactions, which is okay, this is fine. But then you also need way more ancillary variables to compare to a QUBO formulation, and then you run into problems with the exact diagonalization and actually numerically calculating the energy gaps and so on. So this is why we stuck to third order. But
I completely see why you stick to third order, and I completely support that decision. But do you think it's likely that the optimal order of interactions you need for solving k-sat is k?
Okay, I mean, this is an interesting question, which I guess from our results, you can't really extrapolate it. But yeah, I mean, you could, I guess, for very small systems, as maybe compare 4-sat to 3-sat and see how it compares. But yeah, it's hard to say.
Yeah, agree. Okay, Craig has a question. Go ahead, Craig.
Yeah, so this is perhaps a comment. I mean, when I used to spend some time solving large eigenvalue equations on a classical computer, just with matrices sort of around 10 million, and we used something called polynomial acceleration, where we'd apply a polynomial to the matrix to just split the eigenvalues up so they're more spread out, and that would accelerate the speed of determining the eigenvalues. So that's a completely classical technique. Is there any connection between that and this, or?
I mean, I'm not sure if you, I mean, maybe you can, I'm not familiar with the methods, but what we did is basically translate the Hamiltonian into a matrix and then use typical state-of-the-art sparse matrix solvers to get the eigenvalues. So, I mean, maybe you can also do some tricks to improve that, but I mean, we are running here at, for example, QUBO with 12 variables corresponds to a PUBO with already around 19, 20 qubits. So much larger than that, you can't really get anyway, at least on normal machines.
Okay, thank you.
Any other questions for Sebastian? If not, let's thank Sebastian again. Thank you very much. Very interesting presentation. And we'll conclude there. And I look forward to seeing everyone at next week's INQA seminar. Bye, everyone. Thank you, Sebastian.
Thank you. Thanks for inviting me.